Now I want to continue our discussion about the subspace topology. Okay, so the first thing is to talk about closed subsets of a subspace. Okay, so again we're going to let X be a topological space. Y is a subset with subspace topology. And I might also just say, Y is a subspace of X. When I say Y is a subspace of X, I mean, it's a subset of X, and we're considering it as a topological space using the subspace topology. That's what that means. Okay. So let's recall the definition. A subset V of Y is open if and only if there exists some U open in X. With V being a U intersect Y. And so now we're going to have a proposition. A subset G of Y is closed if and only if there exists F closed in X with G is F intersect Y. Okay, so the thing about open sets is the definition. The thing about closed sets is something we're going to deduce from the definition. Okay, so firstly, well, let's suppose G is a closed subspace of Y. Okay, and remember what that means in the context of topological spaces. To say that a subset is closed just means the same thing as to say that the complement is open. So that means that Y with G removed, that's open in Y. And then when I say open in Y, of course I mean open with respect to the subspace topology. So that means there exists an open subset U of X with Y less G equal to Y intersect U. And now we're going to put X, so we put F is X with U removed, complement of U with an X, which is closed in X. Yeah, that's the definition of what it means. It means to say something's closed. To say something's closed is just the same as saying complement is open. Okay. Then you've got some Y lies in F intersect Y, if and only if Y is in Y and Y is not in U, if and only if Y is in Y and Y is not in U intersect Y, which is Y less G, and only if Y is in G. Okay. So F intersect Y is equal to G as required. And conversely, so suppose the other way around, that G is a subset of Y and G is equal to F intersect Y for some I suppose it's the intersection with Y of some set F that's closed in X. So then again, the set U, which is X less F, is open in X. Therefore, the set V, which is Y intersect U, is open in Y, and therefore the set Y and remove Y intersect U which is y less v, is closed in y, but it's easy to see that y with v removed is the same thing as just working backwards through all this, it's y, and I remove y intersect u, but y, and I remove y intersect with the complement of f, and that's just going to be equal to y intersect f, which is g, so g is closed. Okay, so that shows that the way that the closed sets in Y, they work in basically the same way as the open sets. Okay, so now I want to consider another sort of special thing about subspace topology, which goes like this. So, so let's do a picture first. Okay, I mean here's our x, say, and here's our y. And so this you might think of as kind of being a typical situation where y is just some kind of thin subset of x, and here's a set v. So this v is open in y, which means that it can be expressed as the intersection of some. Here you've got v is open in y, v is y intersect u with u open in x, but v is not open in x. Okay, I mean, say that something, in this kind of situation where x is just part of a plane, right? An open set has to be a union of small disks, but there aren't any disks contained in v. V is not at all open. Okay, so that's kind of what you might think of as being a typical situation, but we could have a different situation. Here y was just like this vertical line, but we could instead have like y being equal to this whole sort of left-hand part here. Now in this situation, where this is an example where y itself is an open set. Okay. So now a kind of typical open subset of y might be like this, and that can be expressed as the intersection of we can expand it out to be a, if we want, we can expand it out to be a u here, right? So here's our v, and v again is u intersect y. But in this case, v. There's not really so much difference between things being open in v and open in x. Okay, in this situation where y is open in x, let's just write it down, and v is a subset of y, then here's the claim, right? If you've got in the case where y itself happens to be an open set, then for a subset v to be open in y, it's the same as being open in x. Okay, and so let's first do it one way around. Suppose v is open in y. That means that, as in the picture here, v is equal to u intersect y for some u open in x. But both here u and y are open in x, and intersections of closed of open sets are open. Intersection of any two open sets, or any finite list of open sets, is open. So v is open in x. It's an intersection of these two sets, u and y. U and y are both open in x by assumption, and so v is open in x. And conversely, suppose that v is open in y. And so v is contained in y, and v is open in x. So we want to claim that V is open in Y, i.e. there exists some U with U open in X, and V is equal to U intersect Y. But we could just take U to be equal to V. U is open, in that case, I mean V is open in X, so we can take U equal V, and then U is open in X, and then V intersect Y, in that, U intersect Y is just equal to V intersect Y, but V is a subset of Y, so it's just the same. Okay, so that shows that in the case where you've got an open subset, the subspace topology works out in this rather simple way. And another claim of similar type, so we want to say, suppose that Y is closed in X. And that G is a subset of Y. So then I want to claim G is closed in Y if and only if G is closed in X. Of course, here we're strongly using this particular assumption that Y itself is closed in X. And the proof is basically similar to what we had before. Well, it's just one half of it maybe. Suppose G is closed in Y, then G is equal to F intersect Y, some F with F closed in X. But intersections intersections with closed sets are closed, therefore F intersect Y is closed in X, i.e. G is closed in X. And we've still got to do the converse, but I think I won't go through that. That's the same as in the previous proof as well. Okay, and that will do for this video.